In this video, we talk about a new components I noticed lately from Texas Instruments. It's INA1x9 High side measurement current shunt monitor. Basically, it's a current monitor or current measurement device. It's very easy to use. First, a few features here. And first, it's a unipolar high side current measurements. Okay, it's only can measure one direction of currents, so it's a unipolar. And the high side means it's all the above the low side. We'll talk about that later. Another one is very important feature is wide supply and very can accept very wide common mode voltage. Okay, that's extremely important if you do high side measurements. And very easy to use, just set the gate with a single resistors, very low quiescent current, and it's a 5-pin sort 23 package. So here's a typical typical circuit diagram. If you notice, the load is here, it's connected to the ground. So this is the low side. If you have the current shunt in here, it's low side, but we are here on the high side. Above the load, the current shunt resistor is here, it's below between the voltage input and the load. So it's a high side. So we will talk about this more in a minute. Just quickly go through the features. So it's 5 pins. You get ground output current and power rail and the plus minus input. Okay, let's go. Okay, the full scale sense voltage, the maximum is 500 millivolts. Okay, so that's decide what kind of current sensing resistors you can use. You don't want to over this limit. And they have two versions, 139, 169, and the differences is the maximum common mode voltage is different. Okay, common mode voltage basically is you have a V in here, you have a current shunt to load to ground. Okay, this here, the voltage here, it's very because it's very small values. The voltage here is very little difference. So the basically common mode voltage will very close to your input voltage V in. And very good common mode rejection. That's particularly important because what we are doing is measure differential voltage on top of very high common mode voltage. So the common mode rejection is very important. 120 dB, that's basically 1 in a million. That's about 1 ppm. Offset voltage, reasonably small. Temperature coefficient, 1 microvolts per degree C. That's reasonably good. This is something like offset voltage. You actually can calibrate that, but like the offset voltage drift over temperature, you cannot really calibrate or not easily to calibrate. So this is particularly important. Output gain is not very important here. And the bandwidth, okay, it depends on your applications. If you want to see very dynamic current change, you should think about this bandwidth. This bandwidth is also decided by the resistor, the load resistor or the output side. So that's bandwidth. Say if you have a 1 kilo ohm load resistor, you have a very large bandwidth. Otherwise, you increase the value, you go lower bandwidth. Okay, the load resistor basically means, let's go back to here, this resistor. Okay, the output is a current. To turn into a voltage, you have to pass the current to a resistor to convert that into a voltage value. Okay, let's go back to the. Okay, that's all fine. The operation principle, we'll talk about that in a minute, and all the stuff here. Yeah, also you can have output filters. You put a capacitor in parallel to the load resistance. So you have a simple low-pass filter. And here's offsetting the output voltage. What happens if we want to offset the output voltage, right? Because if no current, ideally if no current, this will output 0 volts. 0 volts, if you have a 0 to 5 volts power rail system, 0 volts is usually not very good measure because very close to the ground, to a limit of the measurement system. So you want to offset the output voltage. Let's say you can offset is to 2.5 volts, for example. Then the 2.5 volts is much easier to measure. So how do you do that? You can very easy to just use a voltage divider here. So you can put a bias current or bias voltage to the output, and all the output will be on top of this biased voltage. Okay, the bias voltage let's see, where the user the bias voltage V bias in this case is basically just the voltage divider. So it's VR divided by R1 plus R2 times R2. And your output will be plus add to this bias voltage. It will be the current times sensing resistor and also times the gain. Another way to do this is this is a tip used very simple way. Another way to do this is to have a current source. Okay, for example, this RDF 200 current source will have a precise 100 microamp output current, and this current will also flow through this load resistor, and your measurement current also flow this resistor, so the value just add up. But this current will be bias. This current 100 microamp times RL will be your bias voltage. So this is just basically just offset your 0 output, 0 volts output, 0 current output to a higher values. So it's good for the measurement system to do the measurements. And as we said, this is a unipolar device, so you only can measure the current in one direction. How do you do if you want to measure two currents, bidirectional current? So if you, for example, you monitor the current from a motor, so the current can go one way, also go another way. Very easy. You just put two devices like this, but connection to the opposite side of this sensing resistor. Then you can do the two bidirectional current measurements. And you will need some kind of diode here in case when you have a current going in this direction, this is 0 volt, 0 current output. You don't want the current to flow back into this device. And you also need a comparator to tell you which direction the current is at a certain moment, if you really care about that. Okay, this is still bipolar current measurements. Okay, that's all good. The very interesting things when I read this first, I noticed is this in the very beginning this circuit. If you notice, this circuit to the feedback loop is connected to the non-inverting input. Is this like what happening here? Is it positive feedback or negative feedback? Is this going to oscillate? So that's what I'm going to analyze. Okay, I copy-paste this circuitry in here. Let's analyze this circuitry, see how that works, and also try to understand, is this a positive feedback or negative feedback? Okay, so here is a circuitry, and let's redraw this in a different way here. We have Vin, the input voltage, and start from here, go to the current sensing resistor, RS, and go to the load, and go to the ground. Okay, then we take the voltage, we try to measure the voltage from these two sides, two nodes right here. So we take that, go through the resistor, let's call this resistor R0, they are usually same values. And go here, go to the op amp, let's go to positive and negative feedback. And the output drive a MOSFET or transistor here, and have a load resistor, we call it RL. Here's V out is the output voltage. This RL turn the current into voltage, and uniquely the feedback is come from the collector of this transistor, or we go back to the non-inverting input. Okay, let's first analyze how this circuitry work. Okay, how just basic try to derive the transfer function. And okay, let's assume this node we have a voltage and V1. Because this is op-amp and no current can flow this direction, no current can flow in. So here, this node also V1. Op-amp principle also tell us if this is V1, this must be V1, because it's gonna be the same potential. Otherwise, op-amp would not be stable. And so now the current, what happens? The current go through this sense resistor I. Let's call that I. I equals to V in. Okay, let's write here. The I current goes through that equals V in minus V1 divided by RS. Okay, V in minus V1, the voltage difference between these two nodes, and divided by RS. That's the current. And this is the current we want to measure. Okay, and we can find the current flow this direction, and also have current flow this direction. No current flow here. And what's this path? So we can see V1, V in minus V1, that's the current, that's voltage potential between these nodes, and divide by R0, that's the current. This current will V in minus V1 divide by R0, that's the current. This current will nowhere else to go, how to go this path, goes through the MOSFET or transistor, goes to the RL. Okay, so the output voltage, this is the current, output voltage will be the current times the load resistor, that's output voltage. Okay, so what happened really here is we kind of really essentially we force the voltage potential between past this RS, we force this voltage potential transfer that to over RL. That's basically the op-amp is doing here. Okay, let's clean up a little bit here. RL, yes. And remember we have the V in minus V1 divided by RS basically is the current in the system we want to measure. Let's move this to here, so that's V in, from here V in minus V1 equals I times RS. So we can replace the V in to this equation here. So the I times RS divided by R0 times RL equals V out. Okay, so the output from this node here or here, so output equals I times RS, the source, the current shunt resistance, and the load resistance divided by this R naught. Okay, so this is the transfer function of these systems. Okay, and the gate, the surface, the circuitry gate basically is these parts. That's basically transfer the I into a voltage output you can measure, go to ADC. And RS is used to be very small, so essentially the gate is decided by the ratio between the RL to R0, R0. You can choose that. Okay, then back to the tricky question we asked in the beginning: is this a negative feedback or positive feedback? There's many ways to analyze this. I'll go to the very straightforward, easy way. Let's just assume the output here goes up. If the output here goes up, then the transistor will conducting more, so there will be no more current go through this transistor or MOSFET. Okay, so that's if the gate voltage or the base voltage goes higher, the current will go higher. Here is a fixed, that means the current here is go higher and the current go through R0 is higher. If the Vin is a fixed voltage, not going to change, how do you make this current go higher? That means V1 here must be goes lower. So the V1 must drop. So the V1s go lower, and this is a non-inverting voltage. When this transfer to the output, that means also the output, force of output go lower too. So we assume go higher, go through the feedback loop, this actually go lower, so they cancel each other. So that means this system is stable. It is a negative feedback. Okay, the takeaway here is, although you have looks like a feedback loop connected to the non-inverting input, it doesn't really mean it's a positive feedback. You have to analyze a system like this. Okay, I think this is about this very interesting device. Hopefully this can help you to understand this device better.